All right. Greetings, everyone, and welcome into my channel. I am Professor L. And remember, this is a live stream for math help. So my intention behind having a live math time is that maybe I would have some students that I could possibly help. There's no reason why anyone today should be bad at math or having insecurities about math. So hopefully, maybe I can help somebody in real life. I haven't had any students yet, but I will go ahead and admit that I have a very sharp learning curve. Yesterday, whenever I left the meeting, I noticed that there was a chat. It said one chat comment and I couldn't figure out how to read it. So hopefully I learned how to use the chat and am able to support some students through this platform. All right, enough of that. So if you do have a question, post it in the chat and well, specifically about your math, that is, and I will do my very best to answer it. All right, so with that said, I'm going to go ahead and get into what I want to present for today. And again, this is me informally trying to get back on the math wagon because I'll go ahead and admit it's been a while since I've visited this subject and been working on my math. I've kind of gotten lazy. And so I'll go ahead and get into it. So yesterday I talked about and introduced this concept called negative angles. And negative angles, remember when you have a negative value out in front of your number, it's signifying a direction. So it still has its same quantity or its same value, whatever number it may be. However, the direction is also important, and that's what that negative is doing. It's keeping track of the direction, and the direction is directly in relation to the origin. And so I'm just kind of digressing a little bit about yesterday's lesson. And after I introduced negative angles, I started talking about this thing called domain and range. Okay, and function and non-function, and how do you tell a difference between a relation and a function? And I really don't think that I did a very good job of explaining that. So I'm going to do my best to kind of start there. And I want to introduce this thing called inverse trigonometric functions. But before I can do that, I feel like I need to kind of explain what an inverse is and what it does and how to generally find one. Okay. And in basic concept in math, not necessarily dealing with functions, just math operations, there's inverse operations. And what essentially inverses do is they take a value, you perform a math operation on it, and then you perform the inverse, and that inverse is going to return your original value every time. And the most basic example of that, okay, most basic example would be the additive inverse. So I'm just going to begin by just sketching some common inverses that everyone should be familiar with, okay? And the first one is the additive inverse, okay? So inverses. Functions. I must have picked a squeaky marker today because this one's squeaky. but I'll just try to deal with it. All right, so what about the additive inverse? So for example, if I have a quantity 1 and I add 4 to that quantity, it's going to give me the quantity of 5. Well, 4 has an additive inverse and it's -4. So if I subtract 4 from 5, I'm going to get my original value back because I performed the additive inverses. Okay. Another one is so this is the additive. There's another common one. The next common one would be multiplication. So it's the multiplicative. See if I can spell it right. So you've got the multiplicative. So for example, if I take the same value and I say 4 times 4, and we know that to be 16. Well, if I perform the multiplicative inverse on 16, essentially multiplying 4 by its reciprocal, okay, then I'm going to divide 16 by 4. 16 divided by 4 is 4. Okay. And so I'm getting my original value because I'm performing an inverse operation. Okay. So this is lower level math. And then in upper level math, you start in like pre-algebra, algebra 1, and you're learning your basic rules. So you're learning all the rules that you need to basically play the game of pre-calculus and calculus. So in algebra, you basically build your foundation. You learn all of the rules. You know, you can't play the game unless you know the rules, right? And that's good for like Monopoly, or if you're playing any of those board games, you go and you know, you read the rules and then you kind of play, and you might be rusty at first. You play a couple times and then you get good at it. Well, it's the same thing with mathematics. You learn the rules in algebra, and then after you get a good solid foundation in the rules, then you can advance forward and start applying these rules in more advanced topics, in advanced settings. So one of the first concepts that you learn in algebra is this thing called radicals and exponents. So you have you learn about and I'm not even sure what this is called, but exponential would be so if you have, for example, the square. So we'll just do the square function. Example of the square function. Because I'm not trying to. I'm gonna switch my marker out. That's squeaky markers probably putting somebody off out there. All right. Not that I have any participants yet. Week 2, we'll see. I'm hoping that eventually I'll get somebody, and another, and one leads to another. Hopefully I'll have a whole room full of people that want to hang out and do math. Okay. I don't know. We'll see. All right. So for example, the squaring function. Okay. And what you have is so we'll just take x, and I can square x. If I want to originally get x back, then what I'm going to do is I'm going to take the square root of x squared. And so these are just basic general examples of inverses. What they do is they're always returning that value, that original value that you gave it. So what it's doing is it's when you invert something, you're just returning the original value of whatever you put into the operation originally. And so these are math inverse operations. And then with functions, however, and so whenever you have a relation that actually is functional, they produce graphs and they have a behavior. Every function has a graph and it has a pictorial representation of what that function is doing, what it looks like. And so in math, we evaluate upper level math, we evaluate these functions in pretty depth and in pretty heavy depth. Okay. And so not every function is going to have an inverse. Okay. We're talking about, so there's a relation. A relation is just a set of ordered pairs. And it could be, you can have a pictorial representation of it, but then you notice that not all, some relations actually have are functions. And what I mean by functions is you're gonna have a table, and it's not, let's see, trying to simplify this. You're not going to have any repeating x values in your function. So for example, we're just going to take the linear function. It's the basic 1 degree or first degree function. You have the linear. And so we'll just talk about the linear real quick. And linear functions, they have inverses because they're 1-to-1, but I'll just show you an example. So let me come up with just a real quick off the top of my head. So we'll say y equals x. Well, I want to have a slope. Hang on. I'll say 1/2. I want it to be positive slope, so we'll do 1/2 x plus 3 or something. That sounds good. And we're going to go ahead and set a table of ordered pairs. And side note, it's probably going to take me 2 days to explain trig inverses. So I apologize. I realize now I'm not going to be able to get all of it because I have to explain what inverse functions are, what they look like in the graph. Okay, so we're just gonna play the game of graphing this function simply, and really I just want to know what's going on around the origin usually. So I'll just pick my 3 favorite points for graphing any function that's I know that is going to go through the origin. Okay. So, or it's not going to go necessarily through the origin, it's going to cross the y-axis at 3. So what I will do is I will just pick -1, 0, and 1. And again, the game is you pick values for your in your domain, and then you evaluate it, and then that's going to give you kind of the range. So what I'm doing is I'm taking these 3 points in my domain, and I'm going to evaluate my function and figure out. And really, with a line, you need a minimum of 2 points to establish behavior. Most other functions, you need a minimum of 3. So I usually we'll just do 3. So we have 1/2 x, and I'm just plugging in for x my value. Okay, -1 plus 3. And so it's going to lead to this ordered pair. And I wish I would have picked an easier point, but that's okay. Negative 1/2 plus 3. And then I'm going to add my fractions, get a common denominator. 2 is going to stay negative. 2 goes into 3. That's going to be 6. So I've got 5/2. 6 minus 1 is 5/2. So I had -1 and 5/2. And then I am terrible at coming up with examples, so I just pulled this out of the top of my head. So we'll just go with it. So we have 1/2 x. So I'm plugging now in 0, and I'm going to evaluate this function. And 0 plus 3 is just 3. And that's my y-intercept. And then I've got one more point when y is +1, 1/2 times 1 plus 3. And that's 1/2 plus 3. And then you're going to add fractions, get your common denominator of 2. You got 1 plus 6 is going to give me 7/2, I believe. Can't write upside down too well. So I've got that's an equal, not a negative. I realize I get a little sloppy. I didn't even spell restricted correctly at the end of the show, the session, whatever this is called. I apologize for my informality and my brevity. Hopefully we'll get better. We'll just see. Okay. So 1, 7/2 is on my graph. Okay. And so I've got these 3 ordered pairs. I'm going to graph this function. And to be honest, I would rather have whole integer values and clean numbers, but that's okay. I can deal with fractions. And to be honest, fractions are not fun for people, but after you spend enough time, I think what really got me liking fractions and being okay with the fractions was whenever I was going through linear algebra and I had to solve matrices and linear equations. Those really will get you on the fractions. So, all right, so I have these 3 ordered pairs. And if I wanted to just sketch real quick, I want to make this kind of big because I'm going to put the inverse on here too. So, yeah, I was planning my lesson because I really want to talk about the trig. And inverses is a really important concept when you're solving trigonometric equations and transferring. Well, there's this thing called the circular coordinate system. So it's kind of like the Cartesian coordinate system, except for it's in a circle in references to an angle and radius. And you have to use those inverses to solve the trigonometric equations, and going back and forth from your rectangular coordinates and your circular coordinates. And so I'm trying to get into some more of the advanced math because that's the math that I'm missing. And so, but I realized that it's not fair to, I'm going to try to explain this in the best I can, like the whole concept. So we'll just see. Maybe I'll fail miserably, and who knows, maybe I won't. All right, so we've got our basic graph. And I'm going to go ahead and just plot these points. And this is x, y, where you will, in a coordinate system, what you're doing is you're going to graph your x component first and your y component second. That's why it's called an ordered pair. Is because there's order to it, first and last type of thing. So we've got -1, 0, and +1. Those are the values that I picked to evaluate this function in my domain and the domain of the function. But I have to figure out what 5/2 is. And if I didn't know, I would just divide it. I would just get like a decimal approximation because I'm just trying to figure out where approximately this function lands, okay? It's not 3, it's 2, Leah. Okay, 2.5, okay. So I'm at -1, 2.5 is going to be, so we'll call that 1, that 2, that 3, then 2.5 should be nested right in there. So I'm just going to draw my dot right there. Okay. And my next one is a little bit easier because I've got 0,3. It's a clean integer, so I don't have to wing it as much. And I'm right there when x is 0, y is 3, and it's my y-intercept. And then I've got +1 and then 7/2. I got to figure out what 7/2 is. And if I didn't know what 7/2 was, then I would just divide it in my calculator. And that it tells me it's 3.5. So we're going to come out here to 1, and I'm going to go ahead and say, well, if that's 4, then maybe 3.5 is right in there. And then it's at 135. So I'm going to go ahead and draw my dot there. And what this is doing is it's giving me, and I'm going to dot this one. Okay, I'm going to dot this one. Because what I'm trying to do is show you a picture of an inverse and what it looks like in the graph. And it's okay if it's not a clean, but it's general behavior of the graph, okay? And it's an increasing function. It's going to a diagonal line. And so basically, when you go to decide whether a function or a relation is a function, what you're doing is you're looking specifically in your domain and you're looking for repeating values. And you can actually go and you can do this. What you're doing is it's a vertical line test where you go and you determine, well, is my is it functional? Is there any place in my graph where if I draw vertical lines in this graph where it's going to cross more than once? And that would lead to repeating x values, right? So if there were 2 -1s or 2 zeros in your domain, if it's an ordered pair and you're looking at this list, you can determine whether it's a function or not, because you can see here that there's no way that there's ever going to be 2 values in your domain that are duplicates, okay? So this is a function. Well, if this function is invertible, okay, then you would not have repeating values in your range either, okay? So you're looking at, in order for the function to be invertible, it's called one-to-one correspondence. So what it's saying is each value in your domain is going to give you a unique, individual, different value in your range. And if you can put your graph, or you can put a table of values into a one-to-one correspondence specifically, then it is invertible and it has an inverse. And what the inverse is doing actually is pretty cool. It's going to establish, and I don't know if this is a very good one because I wish it had a little bit more curve. That's okay. So there is an identity function, which is also, let's see if I can get this exact. What it is it's a perfect diagonal line that goes through the first and third quadrant, and it's called the identity function, and it is a linear function. So we have the identity function, okay? And all it is y equals x. So every value, for example, here, 1, when x is 1, y is 1. When x is 2, y is 2. When x is 0, y is 0. When x is negative 1, y is also negative 1. And you see all those points show up on the graph of this line, and it's called the identity function because they're equal. The values are equal. And what it does is it gives you a perfect diagonal through the first and third quadrants. And inverses, okay, see if I can actually put that right. Third quadrants. Inverse functions, all inverse functions have this special quality where it happens from how you find the inverse and the unique relationship of the function and its inverse, but it has perfect symmetry along this line, okay? It's the identity function, y equals x. And I'm not just talking about linear functions. I'm talking about every inverse and every invertible function out there, which there's a lot of them. There's many. They will have this unique characteristic where and it has to do with how you find the inverse. Typically, it's very, very easy to find an inverse. Well, I say easy, it's just a very straightforward, practical method that you brute force. And what you do is you're just swapping out the domain and the range of your original function. Okay. There's also a way, I cannot believe I did that. I erased it, so I have to remember what it was because I erased it. This was, I have to back up, y equals 1/2 x plus 3. All right, I didn't want to erase it and forget it because what I want to do is I want to show you how you would algebraically find the inverse. And this is typically for any function. So if I had the ordered pairs, I could swap them out, which that's what we're going to do. So if I want to graph the inverse function, okay, so this is f inverse of x, okay. We're going to swap out. So the process is you're swapping out so we'll take this function, I'll rewrite it, 1/2 x plus 3. And I'm literally just replacing y and x. So I'll have x equals 1/2 y plus 3. And now I have to solve for y. I have to perform some properties of real numbers and equality and treat this little equal sign and just start undoing the operations, performing those inverse operations. And that's pretty much how you solve. So I'm going to subtract 3 from both sides. And it's going to give me x minus 3 equals 1/2 y, just rearranging. And then I'm going to multiply, performing another inverse operation. 1/2 x is going to get multiplied by 2. And that's going to give me, we'll use the distributive property here. And I've got to multiply 2 times x, which is 2x, and 2 times -3, which is -6. And that's going to equal y. And then we'll just use that property of the symmetrical property and say y equals 2x minus 6. And then last step, you replace y with an inverse notation. And we have successfully found the inverse of this function, okay, 2x minus 6. And so if I want to sketch the graph of 2x minus 6, well, I already have the table here, and I'm going to pick these same three values, -1, 0, and 1, because that's kind of the chunk of the graph that I picked. And I'll evaluate these same the function at the same point and see what happens. So we're going to say f in inverse of 1 when it's -1. That's 2 times -1 minus 6. And it's going to give me, what is that? 2 times -1 is -2 minus 6. What is that? -8. So I've got -1, -8. Wait, yeah, that's right. What am I doing? I need to just slow down and breathe and not get in too big of a hurry. Okay, so we've got, make sure that I did it correctly. Again, it's a lot easier if I have somebody helping me to do the math. It's better all the way around. So we got -8, and then we've got f inverse of 0. So we're going to say 2 times 0 minus 6, and that's going to give me my my y, should give me my y-intercept, okay? Because when x is 0, that's your y-axis. And so that's going to be -6. So that's 0, -6. And then I've got one more, put it in here somewhere, f inverse of 1. And it's going to give me 2, let's see, times 1 minus 6. And that is 2 minus 6, which is, it's like -4. -4. And let's see about graphing it. All right, so let's go -1, -8. Ooh, I'm gonna have to go all the way down here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So let's go and list them. 0, -1, 2, 3, -4, -5, -7, and -8. So we've got -1, -8 down here at this point. And does that look about right? It's a rough sketch, and so it doesn't have to be perfect. You're just getting general behavior. So we got 0, -6. And 1, -4. So we've got this function. See if I can dot this in here. And it looks like I did a pretty decent job of showing that symmetry, but let's get my. And again, it's going to be a rough sketch, but that was a basic introduction to inverses, like a crash course in inverses, because really, by the time you get to trig, you should have a pretty good grasp on inverses, because you've had plenty of introductions by the time you get to trigonometry. Should have anyways. But like me and like so many other people in today, there's holes in the math. So there's concepts, maybe you're absent that day, or for whatever reason life happens. And so even whenever I decided that I wanted to go to college and study math, I didn't really, you don't know what you don't know until you you realize that you don't know it. And I had many holes in my math understanding whenever I got to college. And, you know, and I was a product of the public school system, and I thought I had a pretty good grasp, and I thought I was, you know, excelled at school, but I still had I felt like, anyway, maybe not. All right. So I'm going to go ahead, fresh start this, and start talking about, and retitle it, the trigonometric. Trigonometric functions. I'm going to put inverse functions. We'll switch that title. Inverse functions. And people are like giving me my, you know, feedback on my live stream and this little, what I'm doing with this channel, and, you know, saying, why don't you just post videos and edit them? And I feel like that there's so many videos out there already. And I think that math begs to be taught by real people to real people. And so I don't want to just post a pretty clean video, not when there's already 100 of them out there. I think it's important for you to see it in real time. And I don't want to be perfect, and I don't want to look like I'm perfect either, not on film. All right. So we're going to fast forward to the trigonometric inverse functions. And we were talking yesterday, we did the graph. Let's see, I sketched the graph of the sine and the cosine. And we talked about how the sine function, cosine functions. So you have sine, how they were functional. They were functions, but they weren't invertible because they're not one-to-one. Whenever you have these repeating values in this table, so we have y equals sine x. We're going to start with sine. Let's see if I can remember, if I can build this table from memory. So what we did was we went out and we had to restrict the domain of the sine function. So we'll just start with the restricted domain. And we'll just do those 3 points: negative pi over 2, pi over 2, and 0. And recall we had to restrict the domain of the sine function because although there's not repeating x values, these in the domain, there are repeating y values. So then we sketch the graph. So what we did was we restricted the domain. And I spelled restricted wrong. I noticed that at the end. The domain. And we gave it the domain restriction, and we have to include those points, so it's a bracket. So we're just taking it from negative pi over 2 to pi over 2 in interval notation. Okay. And we did that because of those repeating values. That was the interval that we found is clean, and there's no repeating values. And the range has always been, and this is a bracket because we're including, it's -1 to +1. Okay. And so at negative pi over 2. Let's see, go ahead and just put the 4 corners up here. This is just my real quick makeshift unit circle. So we've got these 4 points. We're going to call this one 1, 0, 0, 1, negative 1, 0, and this one's going to be 0, negative 1. Looks like a 7. Okay. And let's see here. We're going to go and recall. I derived those negative angles yesterday because we needed them. So we've got pi over 2 here and negative pi over 2 here. And then here's my 0 degrees. Okay. And I'm not sure how to represent 0 in radians. So maybe I'll just say 0 pi over 0 pi. All right. So more importantly, at negative pi over 2, we're looking at the, recall, the cosine is the x component and the sine is the y component on the unit circle. So we have a value of negative 1 at negative pi over 2. So we've got sine is negative 1. And then we've got 0. We're at 0 degrees and the sine value is 0. And then we have pi over 2 and the sine value is positive 1. Okay. So kind of sketch this big because I want to put the inverse in here as well. So what we found working with the sine function, what this trig function does is it takes an angle from its domain. So the domain is a set of all of these angles. And what it's producing whenever you plug in, so you're plugging in your domain here into the sine function, and then it's giving you an output, your range, and that's generating a behavior in your graph. And so this is the general nature of sine function. Well, and it's called arc sine. Arc sine or sine inverse, and you'll see it either with the parentheses. So it's y equals sine inverse of x. And in a table of values, what it's doing is it's taking, so recall the process, you're swapping your domains. What it's doing is it's taking a value and it's giving you, so it's taking the value into the domain and then it's telling you what the angle is. Okay, see how I'm just swapping these out? So there's a couple different ways to find the inverse, but the most simple one, I think, is just all you're doing is you're taking the domain and the range and you're just swapping them out. Okay. I don't know what happened. Darn it. I think my camera might be the battery. I thought I charged it. I don't know. All right. All right. Well, I'm probably going to have to end it there and we'll pick it back up tomorrow. Thank you so much for watching, and I hope everybody has a wonderful evening.